The sun is already attacking you. Right now, as you sit there, particles ripped off its surface at over 1 million miles per hour are slamming into the air above your head, deflected by a magnetic field you can't see, by the thinnest possible margin. We don't talk about it because the alternative is unthinkable. But the star we orbit is not a friend. It is a 4.6 billion-year-old fusion bomb that we happen to live close enough to that we get warmth instead of cremation. Move us a little closer and we burn. Let it twitch a little harder and our civilization unravels in 90 seconds. We grew up being told the sun gives us life. That's true. It's also the smallest part of the story. The sun is the most violent object you will ever see with your naked eye. And the only reason you can stand to look at it for half a second is because it's 93 million miles away. Bring it closer, and your retinas would boil before the pain signal reached your brain. This is that story. The story of a star that has been quietly, persistently trying to kill us for as long as we've existed. And that, on 3 separate occasions in the last 14,000 years, came terrifyingly close to succeeding. Start with what the sun actually is. Strip away the metaphors, the children's book drawings, the warm yellow circle in the sky. The sun is a ball of hydrogen and helium plasma about 865,000 miles across. You could line up 109 Earths across its diameter and still have room. If the sun were hollow, you could pour 1.3 million Earths into it. At its core, the temperature is around 27 million degrees Fahrenheit. That number is so far outside human experience that it stops meaning anything. So anchor it like this. A self-cleaning oven on its hottest cycle hits about 900 degrees. The hottest point on the surface of Venus is around 870. Death Valley in July tops out at 134. The core of the sun is 30,000 times hotter than Death Valley, 200,000 times hotter than your oven. And it's not the heat that's the threat. It's what the heat enables. Down there, in that fusion engine, the sun is converting about 4 million tons of matter into pure energy every single second. Not burning fuel, annihilating it. Every second, the sun loses the mass of an aircraft carrier, and that mass becomes light and radiation that screams outward in every direction. Most of it never matters to us, but some of it does, and some of it kills. Stand on the surface, and the first thing you notice isn't the heat, because you don't get to notice anything. You stop existing. Even 100 miles above the photosphere, where the gas is thinner and cooler, your atoms come apart faster than your nerves can transmit pain. The sun is not a place you can visit. It is a chain reaction wearing the shape of a sphere, and the chain reaction is hostile to every form of matter we know how to build. Now zoom out, past the surface, up through the corona, that ghostly halo you only ever see during a total eclipse. Out into the solar wind, the constant breeze of charged particles that the sun is forever spraying into space at speeds between 500,000 and over 1 million miles per hour. This wind doesn't stop. It hasn't stopped in 4.6 billion years. It blows past Mercury, past Venus, past Earth, past Mars, past Jupiter, past Pluto, until it finally fades into the calm of interstellar space, somewhere beyond Voyager 1, over 15 billion miles from where we're sitting. We are not orbiting a star. We are sitting inside a star's exhale. Stop and picture that for a moment. The only reason that exhale doesn't strip the atmosphere off our planet, the way it stripped Mars bare 4 billion years ago, is the magnetic field generated by molten iron sloshing around 1,800 miles beneath your feet. That field is what shields you. That field is the entire reason there is air to breathe. And every so often, the sun throws a punch hard enough that the field staggers. These punches have names. The smallest are called solar flares, sudden eruptions of electromagnetic radiation that travel at the speed of light and reach Earth in 8 minutes. The bigger ones are called coronal mass ejections, or CMEs, which is a clinical term for what is actually happening. A CME is a billion tons of magnetized plasma being hurled off the sun's surface at up to a few million miles per hour. Picture a planet's worth of glowing, electrified gas vomited into space, sometimes aimed at us. It takes 1 to 3 days to arrive. When it gets here, it slams into Earth's magnetic field, compresses it, deforms it, and induces electrical currents in everything we've built that conducts. In 1859, that's exactly what happened. On September 1st of that year, an English amateur astronomer named Richard Carrington was sketching sunspots through a small telescope in his backyard observatory in Surrey. He saw what he described as 2 patches of intensely bright white light erupt from the sun's surface. He didn't know it, but he was watching the most powerful solar flare in recorded history. The CME that followed it covered the distance from the sun to Earth in about 17 hours, which is roughly 4 times faster than normal. When it hit, the night sky over the Caribbean lit up bright enough that miners in the Rocky Mountains woke up and started cooking breakfast, thinking it was dawn. Auroras were seen as far south as Cuba. The telegraph network, the only electrical infrastructure that existed at the time, went insane. Operators reported sparks flying from their equipment. Some telegraph stations caught fire. Some operators got electric shocks. In a few cases, telegraphs continued transmitting messages after the operators had unplugged them from their batteries entirely, powered by current induced directly from the storm in the sky. That was 1859. We had wires, that was all. Now picture the same event today. Modern grids span thousands of miles. A Carrington-class CME hitting Earth in 2026 would induce currents in those grids strong enough to melt the giant transformers that step electricity up and down between cities. Those transformers are not items you can buy at a hardware store. They are custom-built, often overseas, and the queue to replace them in normal conditions is measured in months. A simultaneous failure of hundreds of them is measured in years. A 2013 study estimated that a direct Carrington-level hit could inflict up to $2.6 trillion of damage on North America alone. A more recent risk assessment puts insured global losses somewhere between $71 billion and $433 billion. And those numbers assume we can rebuild. They don't capture what happens to a city of 10 million people when the power doesn't come back on for 6 months. Hospitals run on backup generators that hold maybe 72 hours of fuel. Water treatment plants need electricity to pump. Refrigeration fails. Gas stations can't pump fuel without power. ATMs are useless. The food supply chain, which assumes refrigerated trucks and functioning ports, breaks. The internet, satellite navigation, and most modern communication degrade or stop. 8 billion people who have spent 2 centuries arranging their lives around continuous electricity discover, all at once, what that dependency means. And honestly, this is the part of the story that still gets to me. The infrastructure that keeps you alive was built assuming the sun would behave. The sun has not signed that agreement. So how often does this happen? Carrington-level events seem to land somewhere around once or twice per century, and modern statistical analyses suggest a roughly 10% chance of one striking Earth during this current solar cycle alone. That probability is not comforting. That is the same odds as flipping a coin 3 times and getting heads every time. People have done worse in Vegas and won. But the Carrington event is not the worst the sun can do. Not even close. In 2012, a Japanese researcher named Fusa Miyake was studying tree rings from ancient Japanese cedars when she noticed something that didn't make sense. In the rings corresponding to the year 774 of the Common Era, the level of carbon-14, the radioactive isotope of carbon, spiked dramatically. Trees absorb carbon from the atmosphere as they grow, and the amount of carbon-14 in the air depends on how much cosmic radiation is hitting the planet. A spike in tree rings means a spike in radiation. A spike that big meant a spike in radiation unlike anything anyone had ever modeled. The leading explanation is that something on the sun, sometime around 774, fired off a particle storm roughly 80 times more powerful than the Carrington event. We call these Miyake events now. We found at least 6 of them in the tree ring record, scattered across the last 14,000 years. The largest one, recently confirmed in subfossil tree stumps from the French Alps, may have been more than 150 times stronger than 1859. If a Miyake event arrived this year, the question stops being whether the grid survives. The question becomes whether the radiation itself reaches the ground. Most solar storms are stopped high in the atmosphere. The particles dump their energy in the upper layers, paint the sky with auroras, and never reach you. But the energies involved in a Miyake event push the protons hard enough that some of them get through. Aircraft passengers flying polar routes during a major Miyake event could receive radiation doses approaching what a worker at a nuclear facility absorbs in a year, in a few hours. Astronauts outside the magnetic field, on the Moon, or on a Mars transit would face acute radiation sickness within hours and likely death within days. And the satellites, all of them, every GPS satellite, every weather satellite, every communications satellite, every spy satellite, would be flooded with particle radiation that they were never designed to survive. A recent NASA-funded simulation concluded that a true superstorm could wipe out essentially every satellite in low Earth orbit. If you were watching this happen from the International Space Station, you would see it before you felt it. The astronauts would have minutes, not hours, to retreat into the most shielded part of the station, a small module wrapped in water tanks and equipment racks that absorb the worst of the protons. Down on the ground, you would notice the auroras first. Not the gentle ribbons people drive to Alaska to photograph. Auroras over Mexico City, over Hawaii, over the equator itself, where they have no business being. By the time the auroras reach Cuba, the high-voltage transformers in the eastern United States have already started overheating. Your phone, if you happen to be looking at it, shows no signal. Then the lights flicker. Then they don't come back. There's a fact that almost nobody outside the field knows. The most likely date for a Miyake event, statistically, is not centuries away. The mean recurrence time, based on the 6 confirmed events, is around 1,000 to 1,500 years. The last confirmed one was in 993. Do that math yourself. And we still haven't talked about what's coming. The Sun is currently in solar cycle 25, the peak of which arrived in 2024 and 2025. May of 2024 brought the strongest geomagnetic storm in over 20 years. A G5 event that knocked out GPS in tractors across the American Midwest during planting season and sent auroras down into Florida and Texas. October of 2024 produced another G4. November of 2025 produced 6 X-class flares in a single week. None of these were Carrington level. None of these were even close to Miyake level. They were the warm-up. There's one thing I haven't told you yet. I've been holding it because it changes the whole frame. The Sun is getting hotter. Not on human timescales. You aren't going to notice anything in your lifetime. But the Sun has been gradually brightening since the day it ignited, and it isn't done. About every 100 million years, the Sun's luminosity climbs by roughly 1%. In another billion years or so, somewhere between 600 million and 1.1 billion years from now, the Sun will be bright enough that Earth's surface temperature crosses a threshold the oceans cannot survive. Water vapor will start filling the upper atmosphere. Water vapor is itself a greenhouse gas. So the warming accelerates. The oceans don't just heat up, they boil, they evaporate. The water molecules in the upper atmosphere get split by ultraviolet light into hydrogen and oxygen, and the hydrogen, being the lightest element, escapes to space. And it's gone. Forever. Earth becomes a second Venus. Bone dry, choking on its own atmosphere, 870 degrees Fahrenheit at the surface, lifeless. That's the slow death. The fast death comes later. In about 5 billion years, the Sun will exhaust the hydrogen in its core. The core will collapse and heat up further, and the outer layers of the Sun will expand outward into what astronomers call the red giant phase. The first thing the swelling Sun will do is swallow Mercury, then Venus. Then it will reach for Earth. There's some debate about whether the Sun's atmosphere actually engulfs Earth, or whether tidal forces drag us in slightly before contact. The end result is the same. Whatever is left of our planet, melted, irradiated, stripped bare, eventually gets pulled into the body of the dying star and ceases to exist as a coherent thing. Earth doesn't end. Earth becomes part of the Sun. You won't be there to see it. Nobody will. Earth will have been uninhabitable for at least 5 billion years by then. Sterilized first by rising luminosity, then by the boiling ocean phase, then by 1,000 smaller catastrophes. The Sun does not need to throw a tantrum to kill us. It just needs to keep doing what it's doing, and in the meantime, every day, all day, the attacks continue. A typical solar wind blows past your body at 900,000 miles per hour. About 100 trillion neutrinos from the Sun's core pass through your eyeballs every second. Most of them go all the way through the planet and out the other side without interacting with anything. The Sun is bombarding you with subatomic particles every moment of your life. And the only reason this doesn't matter is because most of those particles ignore matter the way a ghost ignores walls. But not all of them. The ones that matter are the charged ones. And those are the ones the magnetic field is fighting, right now, while you're listening. Imagine you're standing in your backyard at noon on a clear summer day. The sun feels nice, warm on your face. That sensation of warmth is what an unstable, billion-year-old fusion reactor feels like when you experience it through 93 million miles of vacuum, several thousand miles of atmosphere, and a planet-wide magnetic shield that's deflecting roughly 99% of what's aimed at you. The remaining 1%, the part that gets through, is the part you call sunlight, the part you sunbathe in, the part you photosynthesize gardens with, the part that, given just a little more access, would sterilize you in minutes. We have built our entire mythology of the sun on that 1%. The Greeks thought it was a chariot driven across the sky by a god. The Egyptians thought it was Ra. Every civilization that watched it rise every morning concluded, reasonably, that this thing must love them, because it kept showing up, kept warming the fields, kept making the crops grow. None of them ever saw what was on the other side of the shield. None of them knew that the friendly disk in the sky was actually a self-perpetuating nuclear explosion that, by every law of cosmic statistics, should have killed life on Earth 1,000 times over. We just got lucky. We are still getting lucky. The luck is a daily, ongoing, mostly invisible event. NASA's Parker Solar Probe is currently doing something nobody believed possible 30 years ago. It is flying through the sun's corona, the outermost atmosphere, at speeds approaching 430,000 miles per hour, the fastest object humans have ever built. Fire Parker from Los Angeles, and it would reach New York in about 25 seconds. It is closer to the sun than any spacecraft has ever been, less than 4 million miles from the surface at closest approach, and it survives by hiding behind a carbon composite heat shield that bakes at over 2,500 degrees Fahrenheit on the sun-facing side, while the instruments behind it stay at room temperature. The shield is about 4.5 inches thick. That is the only thing between a billion-dollar spacecraft and instant destruction. 4.5 inches of carbon foam, and the rest is physics. We sent it there because we don't really understand how the sun works. We don't fully understand why the corona is hotter than the surface beneath it, which makes no physical sense. The surface of the sun is around 10,000 degrees Fahrenheit. The corona above it, the layer further from the heat source, is around 1.8 million degrees. That is the equivalent of standing next to a campfire and finding the air 10 feet away hotter than the flames. Nobody has a complete explanation. We don't fully understand why solar wind accelerates the way it does. We don't fully understand what triggers a flare versus what triggers a quiet day. We are, in the most literal way, studying our own murderer to figure out when the next attempt is coming. There's one more thing worth knowing about our star, and it's the part that quietly worries the people who study it. The sun is what astronomers call a quiet star. It is statistically stable. It does not appear to be a flare star, the kind of star that produces unpredictable bursts of energy thousands of times stronger than normal. And yet, observations of other sun-like stars by NASA's Kepler Space Telescope have found that stars statistically identical to ours do, occasionally, produce what are called superflares. Eruptions 10,000 times more powerful than anything we've ever recorded from our sun. The leading theory is that our sun is fundamentally similar to those stars, which means the same physics could be brewing in our star, on a timescale we don't yet know how to predict. Maybe it happens in 1 million years. Maybe it happened in 774, and we're still finding the evidence in tree rings. Maybe it happens next Tuesday, and you're streaming this on a phone that's about to go dark. This is the position we are in. Not metaphorically, literally. We are an electrified civilization sitting 93 million miles from a fusion bomb that has flared violently many times in human history and would, given the right ingredients in its magnetic field, do so again. We've built a planet-wide nervous system of satellites and copper wires and routers and code, and we've draped it over a globe that depends, every second, on the cooperation of a star we cannot influence, cannot calm, and cannot run from. The sun has been attacking us for as long as Earth has existed. The only thing that's changed in the last century is that we finally built something it can hurt. You go inside, you close the blinds, you turn on a lamp. The lamp works because somewhere, hundreds of miles away, a power plant is converting fuel into electricity and pushing it down lines that lead to your house. The whole arrangement depends on a magnetic field generated by molten metal beneath your feet, holding back a 4.6 billion-year-old fusion engine that has, statistically, a roughly 1 in 10 chance of slapping that arrangement out of existence in the next decade. The lamp does not know any of this. Neither, mostly, do you. And that is the deal we've made. The sun is not the warm yellow circle. The sun is what's underneath the yellow. And what's underneath the yellow is the most dangerous neighbor any planet ever had. And that's it for this video. Thanks for watching, and I'll see you in the next one.